In this module, we will explore the Maxwell-Boltzmann distribution of gas particle speeds. In a gas, particles move constantly and collide frequently, exchanging energy and momentum. Through these collisions, their speeds continuously change. Some particles accelerate while others slow down. Therefore, particles in a gas do not all have the same speed at a given instant. Instead, their speeds span a broad range. To properly understand and describe the kinetics of gas phase reactions, it is crucial to know exactly how many molecules have each specific speed at a given temperature. This is precisely what the Maxwell-Boltzmann distribution of speeds describes. To start, let us clearly distinguish between two terms that we use when describing translational motion of gas particles: velocity and speed. Until now, we have been talking about the velocity of gas particles. Velocity is a vector quantity, which means it has both magnitude and direction. To fully specify the velocity of a particle, we need three components. Usually, we label these components as Vx, Vy, and Vz. For example, we might say that a particle has velocity with components of 100 meters per second in the x direction, 200 meters per second in the y direction, and minus 50 meters per second in the z direction. Because velocity includes direction, it gives a complete description of how the particle moves. Importantly, when we consider gases in the framework of the kinetic theory of gases, we assume that the gas is isotropic. This means that the direction in which a particle moves does not influence its properties. As we have previously discussed, if we average the projections of the velocity of all randomly moving particles onto any selected axis, the result is always zero. This happens because for every particle moving in the positive direction of the axis, there is another particle moving in the negative direction, causing the velocity projections to cancel out. On the other hand, speed is the magnitude of the velocity vector and is a scalar quantity. A scalar has magnitude only with no direction. The speed of a particle is simply how fast it moves, regardless of its direction. It is calculated by taking the square root of the sum of the squares of the velocity components. Unlike velocities, speeds are always positive, and therefore they can never average to zero. The Maxwell-Boltzmann distribution describes how many particles in a gas have speeds within a specific range. Formally, the fraction of particles with speeds between v and v plus dv is determined by the Maxwell-Boltzmann distribution function f of v and is given by f of v times dv. We focus specifically on speeds rather than velocities, because many physical properties of gases depend only on the magnitude of translational velocity, not on its direction. While particle velocities average out to zero due to their random directions, speeds are positive and are generally more useful for describing the behavior of gases. To visualize velocities of particles, we use the concept of a velocity space, which is simply a three-dimensional space defined by the velocity components as coordinates. We will use this figure for illustration. In this velocity space, each particle in a gas at a given instant is represented by a single point. The coordinates of this point are exactly the velocity components of the particle. For example, a particle with velocity components of 100 meters per second in the x direction, 200 meters per second in the y direction, and minus 50 meters per second in the z direction corresponds to one specific point in this velocity space at the coordinates 100, 200, minus 50. The advantage of this representation is that we can picture all the particles in a gas at a given moment as a cloud of points in velocity space. In this way, we can directly visualize the distribution of particles' velocities as points filling different regions of velocity space with varying density. Now we don't have well-separated discrete microstates in velocity space, as we would have in a quantum mechanical system, but we can still point to some similarities. In this continuous velocity space, the volume of a region corresponds to the number of microstates available to the particles in that region. The larger the volume in velocity space, the greater the number of possible ways for particles to have velocities within that region. Even though this description is continuous, the concept is similar to counting discrete microstates. We are effectively counting how many microscopic possibilities exist for the particle velocities. Although we started by visualizing velocity vectors in Cartesian coordinates, it is often simpler and more convenient for our purposes to describe them using spherical coordinates. In spherical coordinates, instead of describing velocities with the components Vx, Vy, and Vz, we use three different parameters. The magnitude of velocity v, which is simply the speed, and two angles theta and phi, which describe the direction of the velocity vector. In other words, we explicitly separate the speed of the particle from its direction. In many situations, the direction of translational motion is not as important as the speed. Focusing on speeds rather than on full vector velocities simplifies our work significantly. Instead of dealing with complicated three-dimensional vector functions, we arrive at a much simpler scalar distribution, the Maxwell-Boltzmann distribution of speeds. To convert the velocity distribution into the speed distribution, we need to consider which region of velocity space corresponds to a particular value of speed. We will use this figure for illustration. In velocity space, we consider a spherical shell with radius v, which represents the speed, and with a thickness equal to an infinitesimally small differential of speed dv. All points on the shell correspond to velocity vectors with magnitudes between v and v plus dv. In other words, they all have the same magnitude v, but their directions are different. The area of this sphere with radius v is given by 4pv squared. If we multiply this area by the shell thickness dv, we obtain the volume of this spherical shell in velocity space. D capital V equals 4p small v squared d small v. This expression represents the differential volume element containing all velocity vectors with magnitudes between v and v plus dv. As we discussed earlier, this volume is analogous to the number of microstates corresponding to speed v. To obtain the Maxwell-Boltzmann distribution of speeds, we combine two key elements. First, the number of microstates corresponding to speed v. It is represented by the differential volume element d capital V. Second, the probability that these microstates are actually occupied. This probability is given by the Boltzmann factor. Specifically, the probability of a microstate with energy epsilon to be occupied is proportional to the exponential of minus epsilon divided by kb times t. Since we are considering only translational motion, the relevant energy here is the translational kinetic energy of the particles. It is given by 1/2 times m times v squared. Here, m is the mass of the gas particles. By substituting this expression for the translation energy into the Boltzmann factor, we obtain an occupation probability that depends explicitly on the speed. Now we multiply this probability by the number of available microstates, which is given by the differential volume element d capital V. As we have seen, this element scales with v squared. After multiplying these factors together, we obtain an expression that contains all the speed-dependent terms in the Maxwell-Boltzmann distribution of speeds. This expression represents the unnormalized form of the Maxwell-Boltzmann speed distribution. The full expression for the Maxwell-Boltzmann distribution must include a normalization constant. To determine the value of the normalization constant, we need to integrate the distribution over all speeds from 0 to infinity and find the value of the constant that guarantees that the total probability of finding particles at any speed adds up to 1 as required for any proper probability distribution function. Without going into detail, after performing this normalization, we obtain the fully normalized Maxwell-Boltzmann distribution of speeds, which is shown here. This distribution can be also expressed using the universal gas constant and the molar mass of the gas. Here we see an example curve of the Maxwell-Boltzmann distribution of speeds. The curve passes through a maximum, which corresponds to the most probable speed. At very low speeds, the probability of occupying a state is high. However, the number of states corresponding to very low speeds is very small. Specifically, at zero speed, the occupation probability is the highest. But there are no velocity states corresponding to exactly zero speed. As a result, the function f of v is zero at zero speed. As the speed increases, the number of available states increases proportionally to speed squared. In other words, parabolically. But at the same time, the probability of these states being occupied decreases exponentially with increasing speed squared. At high speeds, the exponential decay of probability overcomes the parabolic growth in the number of states. Thus, at very high speeds, the function f of v again tends to zero. Now we will introduce three characteristic speeds of the Maxwell-Boltzmann distribution. They are summarized in this figure. These are helpful reference points that summarize the behavior of the distribution. They also represent important physical properties of the gas. The first one is the most probable speed, which corresponds to the position of the peak of the distribution curve. It can be determined by differentiating the distribution function. It is given by the square root of 2kb times t divided by m, or equivalently by using the universal gas constant and the molar mass. The next one is the mean speed, which is the average speed of all the particles. Mathematically, it is defined as the integral of v times f of v over all speeds from 0 to infinity. The mean speed is given by the square root of 8 kb times t divided by pi times m. Finally, we have the root mean square speed. This is the square root of the average of the squares of the particle speeds. The average of the squares of the particle speeds is defined as the integral of v squared times f of v over all speeds from 0 to infinity. The result for the root mean square speed obtained using this formula is exactly the same as obtained earlier when we analyzed the translational kinetic energy of gas particles. The square root of 3 kb t divided by m. Comparing these three characteristic speeds, we see the following order. The most probable speed is the lowest, the mean speed is a bit higher, and the root mean square speed is the highest of the three. If we compare their respective formulas, we can express the ratio between the three characteristic speeds. Taking the most probable speed as the reference, the ratio is 1 to 2 over the square root of pi to the square root of 3/2. Numerically, their ratios are approximately 1 to 1.128 to 1.225. Thus, All three characteristic speeds are of similar magnitude, but not identical. Let us now explore how the Maxwell-Boltzmann distribution changes with temperature. First, take a look at this figure, which shows the distributions for argon gas at two different temperatures, 298 Kelvin and 1000 Kelvin. At the higher temperature of 1000 Kelvin, the peak of the distribution shifts towards higher speeds. This shows that as the temperature increases, the most probable speed of the particles also increases. This implies that other characteristic speeds increase as well. The physical reason is straightforward. At higher temperatures, states with higher speeds become more populated. This shifts the balance between the increasing number of available states and decreasing probability of their occupation, so that their product peaks at higher speeds. As a result, particles are more likely to be found at higher speeds. Moreover, as the temperature increases, the distribution curve becomes broader. This is also connected to the occupation probability. At higher temperatures, the population difference between energy levels with the same energy gap becomes less pronounced. The exponential factor in the Boltzmann distribution becomes less steep, and the distribution spreads over a wider range of speeds. It is also important to remember that the integral of the entire curve, the total probability, is always equal to 1. When the temperature increases and the distribution becomes broader, the peak height must decrease to compensate for these changes, because the total area under the curve does not change. If we look closely at the formula for the Maxwell-Boltzmann distribution of speeds, we notice something significant. Mathematically, the distribution does not depend on temperature and particle mass separately. Instead, these two variables always appear together as the ratio of mass to temperature. This means that increasing the mass of the particles has, in a purely mathematical sense, the same effect as decreasing the temperature. Both changes cause the exponential factor in the distribution to become steeper as the speed increases, and shift the peak of the distribution to lower speeds. However, beyond this mathematical observation, the physical explanation of how particle mass affects the distribution at constant temperature is straightforward. Look at this figure, which shows the Maxwell-Boltzmann distribution for three gases: neon, argon, and krypton at 298 Kelvin. When the mass of the particles increases, the peak of the distribution curve shifts to lower speeds, and the curve becomes narrower and higher compared to that of lighter particles. The physical reason for this behavior is that when the mass of the particles increases, the Boltzmann probability function declines more sharply as a function of speed. For two states corresponding to different speeds, a higher particle mass results in a larger difference in energy. The difference in population between these states becomes more pronounced. Consequently, the increasing number of states is overweighed by the decreasing occupation probability at lower speeds. This results in the observed changes in the Maxwell-Boltzmann distribution.